Hi students, I am Dr. M. Ashraf Majrooh, Professor of Community Medicine. I welcome you in the learning session of Data Distribution. This is 7th session on Medical and Biostatistics. The agenda of this session include a PowerPoint presentation and SPSS demonstration. In PowerPoint presentation, we will discuss what is data distribution, data patterns and statistical distributions, steps for fitting distribution models of probability, normal distribution and z-score, standardization of data distribution, properties of standard normal and student t distribution, properties of binomial and Poisson distribution. In SPSS demonstration, there will be estimation of z-score on SPSS, estimation of probability of standard normal distribution, estimation of probability of binomial distribution on SPSS. Let's take the agenda point one by one. What is data distribution? The pattern and trends of the data depicted through diagrammatic, graphical or pictorial expression is known as data distribution. Distributions are generally used for statistical predictions of probabilities of the event, provided the data of sampled population is following a particular shape and trends. Distribution observed in descriptive summaries of data are extrapolated into inferential statistics to generalize the inferences over the reference population. Statistical tests and statistical operations on data are selected and modified according to the nature of distribution of the data. If the data is fitting into a particular model, then we use the parametric statistics, and if it is not fitting good, then we use the non-parametric statistics. Here we observe the data pattern. The histogram is synergized with the line diagram, and the typical pattern depicted through these diagrams. This is the symmetrical bell-shaped distribution, bimodal distribution, uniform distribution, left skewed distribution, right skewed distribution, and multimodal distribution. These we have described in previous session in detail in data presentation. So mathematical and statistical distribution models. There are about more than 20 statistical distribution models which are particularly named as normal, beta, beta pert, gamma and so on. But we will discuss in detail in this session about the normal distribution. Then we will discuss the properties of student t distribution and properties of binomial distribution and Poisson distribution. So steps for fitting distribution models in prediction of probabilities are p-values. So this is very important to learn about these steps where we fit the statistical distribution into mathematical models. Step 1. Analysis of data and making descriptive summaries according to the types of variables. Then plotting the data in graphical patterns like histogram, bar charts, line graphs, box plots, stem and leaf plots, and so on. Then in third step, observe the data pattern and symmetry of the data. For example, normal, skewed distribution, unimodal, bimodal, and so on, as we have described already. Then in step 4, fit the data pattern into mathematical or statistical model like normal distribution, t distribution model, binomial, Poisson distribution model, beta, exponential, and so on. and then standardize the observed values or data summaries according to the selected statistical model of distribution. And lastly, estimate the probabilities or p-values for confidence limits, hypothesis testing, and inferential decision making in statistics. So these are the key steps for fitting the distribution model for prediction of probabilities. Then we will discuss normal distribution. Normal distribution is most important probability distribution in statistics because it fits many natural phenomena. For example, heights, blood pressure, measurement errors, and IQ scores follow the normal distribution. It is also known as Gaussian distribution and it is bell-shaped curve. So when continuous numeric or class data is plotted by relative frequency and measurement scales, it will produce a smooth bell-shaped curve that is known as normal distribution. So here we learn certain properties of normal distribution. Curve is bilaterally symmetrical. Mean median mode lies in the center of the scale on x-axis. Probability of observed values are maximum at the center, that is around the mean of the data. Probability and relative frequency varies from minimum to maximum. 0.5 is the center to the minimum on both sides. The standard normal distribution curve extends indefinitely in both directions, minus infinity to plus infinity. The cumulative probability is shown by the area under the standard normal distribution curve. Total probability or the area under standard normal distribution curve is equal to 1. Then how we standardize the normal distribution? If we observe the pattern of the data in normal distribution, then we can standardize the distribution. Here is the normal distribution generated from the sample data of systolic blood pressures. So the mean is 110 and the standard deviation is plus minus 16. If we look at this normal distribution, this is symmetrically distributed on both sides, and as we have the standard deviation, so in plus minus standard deviation the probability points are fixed. Now how we standardized? We find the distance in terms of standard deviation, and this distance is measured through z-score. Z-score is the deviation of observed value from the mean estimated in terms of standard deviations. So z is equal to x minus x bar over standard deviation. When we use this z-score instead of measurement scale, then the distribution becomes standard normal distribution. So this is the standard normal distribution. It is generated from the z-scores of the same data instead of measurement scale. So in standard normal distribution curve, the measurement scale is replaced by the standard scale in terms of standard deviation. Mean of this normal distribution is 0 and standard deviation plus minus 1. Area under normal distribution curve, total area is taken as 1. The deviation of each observed value from the mean is converted into number of standard deviation from the mean in terms of z-score. This is known as standardization. Steps for standardization of observed value in dataset. Let's take the example of dataset. Consider a dataset of systolic blood pressure of 10 normal adult women measured in mmHg. Using this data set, let's standardize the distribution of the data fitting into the model of normal distribution. So this is the observed values. These are the observed value in the data set. And how we will proceed. In first step, we find the mean of the data, that is sigma x over n, and in this data set it is equal to 110 mmHg. Next we find the standard deviation, as we have already described in previous session, by the statistical notation sigma x minus x bar square over n minus 1, and this is equal to 15.748 mmHg. So this is the standard deviation. Now what we will do in third step, we find the deviation of each value from the mean in terms of x minus x bar in mmHg. So if we observe this data tabulation, these are the observed values and this is the mean, and this is the x minus x bar indicating the difference of each value from the mean on positive and negative side. If we look at 120 is deviating from the mean value on positive side by 10 mm, and 108 is deviating from mean by minus 2 mm, and so on, and this is the deviation from the mean. In fourth step, we convert the deviation from the mean into number of standard deviation, that is known as z-score. If we look at the z-score, this is this distance x minus x bar is divided by standard deviation. So 10 divided by this standard deviation, we will get the z-score here, and in second column we divide minus 2 divided by standard deviation and we will get this z-score. So in this way we get all the z-scores in the value. And next, in fifth step, we find the mean of the z-score of all observed values of the data set, that is equal to 0. In next, we find the standard deviation of z-score of the data, that is equal to plus minus 1. And if we observe the steps, this is the mean, this is the deviation from the mean, this is the standard deviation, and this is the z-score. And now this is the square deviation from the mean, and then they are converted into standard deviation, and estimated standard deviation of standard normal distribution curve is plus minus 1, and the mean of the standard normal distribution is 0. So this is how we standardized. We can replicate the measurement scale into z-score, and from z-score we can estimate the probabilities. So significance of normal distribution curve, deviation of each value from the mean is standardized in z-score. Probabilities are predicted against the z-score distribution in standard normal distribution. For example, probability at 0 z-score in the central location is 0.5. We can predict the z-score from known probabilities. If 0.95 probabilities of all values are data set, they will fall within plus minus 1.9 z-score. We can inverse and translate the z-score into original values as we know the mean and standard deviation. Probability against z-score and vice versa are determined by using z-tables or computer statistical softwares. Empirical rule of standard normal distribution curve. The distance from the mean and the probability are fixed and constant in terms of z-score of the observation in standard normal distribution. Most of the area lies between minus 3 standard deviation to plus 3 standard deviation scores. Key landmarks for the probabilities in the z-score are, here if we observe within plus minus 1 standard deviation, the data values 68.27% of the data values have the probabilities to fall within plus minus 1 standard deviation. If we talk about minus 2 and plus 2 standard deviation, the area between plus minus 2 standard deviation will cover 95.45% of the data values in the data set. And in minus 3 to plus 3 standard deviation, the probability of the data will be extended to 99.73%. And similarly, if we want to have the exact probability at 95%, then it will be equal to plus minus 1.96 standard deviation instead of exactly 2. So at 0 standard deviation, there is probability of 0.5. So these are the empirical rules in standard normal distribution. Then student T distribution is very important and commonly used in statistical operations. T distribution, also known as student T distribution, is the type of probability distribution that's similar to normal distribution. It is bell-shaped but has heavier tails. The shapes of the T distribution varies with the sample size. With smaller sample size, the tails are fatter. So here we can observe the characteristics of T distribution in comparison to standard normal distribution. There are some similarities and some differences. If we talk about the similarities, it is bell-shaped like normal distribution, symmetrical around the mean, median, mode are centrally located, and curve never touches to x-axis. Then what are the differences from the normal distribution? Variance is greater than 1. The shape and probability varies with the sample size, which is sometimes known as degree of freedom. As sample size increases, it approaches to standard normal distribution. So these are the characteristics of the T distribution, and this is also used in statistical tests. Binomial distribution is very important in a sense. Binomial distribution is used in situation where we want to predict specified probability of success in fixed number of trials. Suppose n number of trials are performed and the probability of success on any particular trial is equal to p. Let's x denote the number of successes in n number of trials with binary outcome as success or failure. The probability of distribution of the random discrete variable x is estimated by statistical expression px, x out of n number of trials, and the probability of success multiplied by probability of failure raised to power n minus x. So what are the assumptions behind the binomial distribution? Identical trials are to be performed. Two outcomes, success or failure, are expected. P is success and 1 minus P is the failure. The trials are independent and the success probability P remains the same from trial to trial. So these are the important assumptions with the binomial distribution. And lastly, the Poisson distribution is modification in the binomial distribution. A Poisson distribution can be used to measure how many times an event is likely to occur within X period of time and named after the mathematician Denis Poisson. This model helps to predict the probability of given number of events happening in a fixed interval of time. The statistical expression is frequency of x, lambda x divided by x factorial, Euler raised power minus lambda, where Euler is the constant and x is the number of occurrences, and factorial x is the mathematical factorial of x. Lambda is the mean expected value of x that is also equal to its variance. So if we observe, if the expected value are the samples, they are increased, then the shape of the Poisson distribution will be similar to the binomial and normal distributions. So these are the properties of Poisson distribution. Now the conclusion. Normal distribution describe the continuous data which have symmetrical distribution with a characteristic of bell shape. Binomial distribution describe the distribution of binary data from a finite sample. Thus, it gives probability of getting X event from n trials. Poisson distribution describes the distribution of binary data from infinite sample. Thus, it gives the probability of getting X event in population. So, these are the characteristics of the various statistical distributions. Now, the demonstration on SPSS. In SPSS, we will find the z-score of continuous numeric data set as given here and find the p-value of the same data set, and then we will find the cumulative p-value of the same data set. Then we find the p-value of cumulative probability of discrete data set of 9 trials, binomial distribution trials. So let's move to the software SPSS. If we go to the SPSS, here we have those two data sets. One is the continuous numeric data of systolic blood pressure of 10 observations, and other is the 9 trials probabilities. We will find the binomial probabilities of these trials. So how we will estimate this? First we will estimate the z-score of the systolic blood pressures. We will go to the analyze and we will go to the descriptives, and in descriptive we will go to the descriptives. Here we click the descriptives and we will select the data of systolic blood pressure, which is the continuous numeric variable, and here we have the option to check in save the standardized values. So here we will get the z values, and we will also go to the options. We will deselect those options which are not required. For example, we don't need maximum, minimum. We need only mean and standard deviation. We will continue and OK. So here you find the mean of the data set is 110 and the standard deviation is this, but where you will find the z-score we will find in the data view. If we go into the data view, here we will get the z-score, and the new variable is created which is indicating the z-score. So the z-score for all values, all these values, the z-score has been estimated. Now we will estimate the probability of each value against the z-score. We will go to the transform and compute variables. In compute variables, we have the dialog box, and here we will find the PDF functions. The PDF function, here we select the PDF functions, and we will select the PDF function for normal distribution, and here in this box we will find the PDF normal. So here we found the PDF normal, and we double click to select this. Here we get 3 question marks. In one question mark we will enter our data value, first question mark. In second question mark we will enter the mean of the data, which we know we have already seen, that is 110. And in third question mark, we will add our standard deviation, that is 15.748. So we will say the PDF, say this is the file PDF, and we will continue and we will click OK. Now where we get the probabilities, here we have the probabilities. We will increase the uh, decimal points. We will increase up to 5. So when we see in the data variable, here is the probabilities are PDF. These are the p-values against each of the values. Now we will estimate the cumulative probability. We will go to the transform and compute function. We will reset our data. We will find the cumulative probability function CDF, and we will find this for the normal distribution. These are those distribution which we have mentioned there in our PPT presentation. This is the normal, and here we select the normal distribution, and again we have 3 question marks. So first is our data set, and we will put this into this, and second is the mean. Mean is 110, and third is the standard deviation. Our standard deviation is 15.748. So this is our CDF function, and we will continue. Again we will click OK, and we will go to the data view, and here we get the CDF cumulative probability, and we will increase the decimal points, and here we have the cumulative probability. So in this data set we have estimated for the continuous numeric data the z-scores, and we have estimated the probability of each z-score, and then we have estimated the cumulative probability. So this is how we can use SPSS for estimation of probability against each value. So this was about the normal distribution functions on SPSS. Thank you very much for sparing your time.